Distinguished guests, esteemed faculty members, all participants, good afternoon and welcome to the 33rd Specialฬาลงกรณ์ University, the Asahi Glass Foundation Seminar 2025. This year is held under the theme, Advanced Materials and Engineering for Societal Impact. My name is Rin Chutikan Pongsarat, and I'm honored to be your MC once again in this special occasion. Today marks a celebration of knowledge, innovation, and international collaboration, where ideas meet action, and we hope to inspire and create real impact on our society. So, on this occasion, we would like to begin with an opening ceremony. To officially begin our opening ceremony, I would like to invite Professor Dr. พรอนงค the Vice President of จุฬาลงกรณ์ University, to deliver the welcome remarks and a brief report. Please welcome.
Good afternoon. สวัสดีค่ะ Mr. Takuya Shimamura, Chairman of the Asahi Glass Foundation, Professor Dr. Willard Puvirat, he's the president. He's going to join us pretty soon. Distinguished guests, let me introduce you. Dating back in 1982, the Faculty of Engineering at Chulalongkorn University received its first support from the Asahi Glass Foundation, which initially focused on engineering research. Over decades, this support has expanded into other key fields, for example, medical, environmental science, information technology, and extended into the social science, together with architecture, as evidenced by the presence of the awardee from the Faculty of Architecture and the Institute of Thai Studies, who are joining us today. Nearly 400 research projects has been made possible. Thanks so much for this partnership. Furthermore, we have regularly held special seminars based on research finding, providing valuable platform for the exchange of the knowledge and expertise between academics and external organizations. These seminars, which have been organized for 33 years, continue to promote the practical application of research across various sectors. This year, we are particularly honored to have Professor Dr. Suwabun Jirachanshay delivering the keynote lecture on the topic Revisit Starch, a Polymer-Based Approach to Functional Material. In this special section, we look forward to exploring how the starch can be used more effectively and gain more attention in the industry. Once again, I would like to express my deepest gratitude for your ongoing support of our research initiatives. Now, I'm pleased to invite Professor Dr. Willard Puvirat, the President of Chulalongkorn University, to deliver the opening address. Thank you very much. Please welcome him.
Mr. Takuya Shimamura, Chairman of the Asahi Glass Foundation, the Executive of AGC, AG Flat Glass Thailand, AGC Automotive Thailand, AGC Winnie Thai, AGC Asia Pacific Singapore, and distinguished guests. It is my great honor being here to have distinguished executive with us today. Your presence here emphasizes the foundation commitment to fostering innovation, supporting groundbreaking research, and contributing to a better society. We deeply appreciate the vision and generosity that the Asahi Glass Foundation consistently demonstrates to this grant that continuously support us at Chulalongkorn University for more than 40 years. Today, we celebrate not just the grant awarding ceremony, but also the powerful partnership between visionary organizations like the Asahi Glass Foundation and the dedicated individuals who are driving progress in their respective fields. We often speak of research and innovation, But here at Chulalongkorn, we also believe in putting the innovator before innovation. If you would like to create great innovation, you have to create innovator. Innovator come before innovation. So this is why we are here. We understand that behind every great discovery and every impactful solution is a brilliant mind, tirelessly dedication, and a passion for making a difference. A notable one is here with us today, our keynote speaker and alumnus of Osaka University, Professor Dr. Suwabun Jirachanchai from the Petroleum and Petrochemical College. Later, you may gain more information from his lecture, how it looked like when a spirit of researcher truly make breakthrough possible. This special CUAF seminar is organized to showcase the research project supported by the Asahi Glass Foundation. We are especially proud that the project undertaken by our talented researcher and innovator embody our commitment at Chulalongkorn for all, ensuring that the benefit of our research and education extend to every corner of society. Once again, I would like to take this opportunity to express my deep appreciation to the Asahi Glass Foundation, and I would like to encourage all of you to engage this event and even build the lasting connection. It's not just about like the ceremony that we are here today. I think it is the partnership that gets stronger and stronger. Thank you very much for your presentation. Thank you very much for your present today. Thank you.
Thank you very much, Professor Dr. Willard Puriwat, for your inspiring words and your kind words as well. Next, we are pleased to welcome Mr. Takuya Shimamura, the chairman of the Asahi Glass Foundation, to deliver a congratulatory address.
Thank you very much for your kind introduction. Sawadee krap. Good afternoon, everyone. My name is Takuya Shimamura, chairman of Asahi Glass Foundation and chairman of AGC Inc. Before I begin, I would like to express my heartfelt sympathy to all those affected by the recent earthquake in Taiwan. Our thoughts are with those who have been affected. Now, will you please allow me to extend my sincere gratitude to President of the University, Professor Willard Puriwat, Vice President Professor Pong Arawi, our distinguished guests, and the members hosting today's ceremony. Thank you very much, Kopunka. And to all recipients today, congratulations on winning the scholarship this time. I also thank Professor Willard Puriwat and his team for taking the time to visit our office in Tokyo and AGC Yokohama Technical Center during your stay in Japan this March. We truly appreciated the opportunity to welcome you. Let me introduce Asahi Glass Foundation briefly. It was established in 1933 to celebrate the 25th anniversary of the founding of Asahi Glass Company Limited. Asahi Glass Company was established in 1907 and to produce the architectural glass, firstly in Asia. After that, Asahi Glass Company extended business area from Japan, Asia, and worldwide. Now we operate more than 30 countries worldwide. Asahi Glass Company Limited was renamed AGC Inc. in 2018. In terms of the relationship between AGC Inc. and Taiwan, in 1964, AGC began to produce flat glass in Taiwan. and expanding its business to automotive glass, chemicals, and electronic materials. Today, total annual sales revenue of the group is approximately $1.5 billion in Thailand, and now about 6,000 employees are working with us. And we are pleased that significant number of the Chulalongkorn University graduates have started their career at AGC Group, such as AGC Flat Glass Thailand and AGC Binitai. Let me go back to introduce the foundation. Now, our foundation provides 4 major programs, which are research grant program, scholarship program, commendation program named Blue Planet Prize, and environmental learning support program for young generations. In 1982, Asahi Glass Foundation initiated our grant program with Chulalongkorn University. This is the first overseas grant program for the Asahi Glass Foundation. So this year, it is the 44th grant presentation ceremony. We have supported 348 grant themes and contributed approximately $2.5 million from the beginning. I believe these research results are contributing enough for the development and prosperity of Thailand. Please visit our website so that you can reach the names and research themes of the grantees and the research reports of the previous grantees. We wish our support can be helpful for your researchers. As one of other major activities of the foundation, we have been awarding Blue Planet Prize since 1992. The Blue Planet Prize is awarded to 2 individuals or teams who have made outstanding contributions towards solving global environmental issues, with a certificate of merit, a commemorative trophy, and $500,000 per each in prize money. This year's Blue Planet Prize laureates were just announced on June 11th. One of the laureates is Professor Robert Jackson, Stanford University in the United States. The other laureate is Dr. Jimmy Leggett. He is founder and CEO of Highlands Rewilding Limited in the United Kingdom, and he was also the first chairman of the Carbon Tracker Initiative. Please visit our website, which explains their achievement in detail. The presentation ceremony will be held in October in the presence of their Imperial Highness Crown Prince and Princess Akishino. They have been supported the Blue Planet Prize more than 30 years. As you know, our environmental situation is getting worse year by year. Humanity has achieved prosperity at the cost of the environment. This is the reason why we established the Blue Planet Prize. I truly hope that one day a laureate from the Thailand will be honored with this prize. I sincerely hope all of the researchers here will contribute to our precious blue planet through your research. Once again, I would like to express my deepest appreciation to President Professor Wida Wuriwat, Vice President Professor Pong Arawit, our distinguished guests, the members hosting today's ceremony and members concerned kindly supported the seminar and award ceremony as well. As closing my speech, I would like to express the following. I firmly believe in for all of you today, your future is bright, your potential is unlimited, and your possibilities are endless. Thank you very much for your attention. Congratulations. Thank you.
Thank you, Mr. Takuya Shimamura, for your kind words and encouraging message. Now we will proceed to the certificate and award ceremony. So in this regard, may I kindly invite Mr. Shimamura once again on the stage, as well as Professor Dr. Willard Puriwat to join us to present the certificates. This grant award ceremony is now to recognize the exceptional contributions of this year's grantees. So to all grantees, as I announce your name, please come forward and step onto the stage to receive your certificate, and kindly pause for a brief photos before we proceed to the next awardee. Please do note that we would like to have 2 poses for each photo session, one with the closed certificate and the other with the open certificate. Also, if there is anything you are unsure of, please listen to the instruction of our photographer. So to start off the ceremony, congratulations to Dr. Kanok Pruti Watanyu, Assistant Professor from the Faculty of Medicine. Thank you very much. Next, congratulations to Dr. Vivittawin Sukmat, lecturer from the Faculty of Science. Thank you very much. Next, Dr. Jirapong Launamsai, lecturer from the Faculty of Engineering. Thank you. Next, congratulations to Dr. Chanun Pon Rungrod, a lecturer from the Faculty of Engineering. Wonderful, thank you. Okay, one more shot. Okay, we do have that. Okay, thank you so much. Next, congratulations to Dr. Sarin Pinit, a lecturer from Faculty of Architecture, represented today by a colleague. Thank you. Next, congratulations to Dr. Sutlop Rattana Gur Kangwan, a lecturer from the School of Agricultural Resources. Congratulations. Next, congratulations to Dr. Jinawat Ganmuang, a researcher from the Institute of Thai Studies. Congratulations. And next, Dr. Panaya Kutchaplai, a researcher from the Institute of Biotechnology and Genetic Engineering. Thank you. Lastly, can we have one more photo? Thank you, wonderful. And lastly, Dr. Pirunporn Simongkon, a researcher professional level from the Institute of Biotechnology and Genetic Engineering. Thank you. Before we conclude, we would like to acknowledge one more grantee as well, Dr. Kitipong Angsutjinda, who is currently conducting research overseas. So we send him our warmest congratulations from afar and will surely ensure that the certificate is delivered to him after the event. And that concludes the award ceremony. Thank you so much. May I invite Mr. Shimamura and also Dr. Willa Puriwat to return to your seats as we proceed to the next session. Thank you. Distinguished guests, it is now time for our keynote lecture titled Revisited Starch, a Polymer-Based Approach to Functional Materialists. For this session, please join me in welcoming Professor Dr. Suwabun Jira Shanchai from the Petroleum and Petrochemical College, Chulalongkorn University.
Okay, thank you very much. It's my pleasure to be here and to deliver my talk. Actually, many years ago, 30 years ago, I was once awarded, supported by Asahi Glass Foundation. So it's something like I come back to the stage and witness the happening that once happened to me. But thank you very much for the long-term support from Asahi Glass Foundation. So with those small or big support that I received from the way through, so today I'm very pleased to share my current work. When I was asked by Professor Bancha to deliver the talk today, I told him that I will talk the new things that I've never been talking to the public before. So the topic is very simple because what I want to do is about the starch. So let me start from the general information of starch. As you may know, that starch in Thailand, most starch come from cassava, tapioca, some from corn, and of course from rice. Well, actually, you may know that starch is white, odorless, and also tasteless. And starch is not soluble in water, in cold water, but in hot water, it will be a kind of gel or gelatin, and also very sensitive to moisture. And normally in food, we use starch in our daily life food and beverages, and also for pharmaceutical like tablets, and also even in pet. And actually not only that, for the non-food applications like paper industry, construction, textile, or even glue. So with those background, starch, if you take a look at starch, you see the granule, which is something like 100 microns. So 100 microns, our hair is about 10 microns, something like that. So starch is quite big granules. And if you look through the granules, you see the crystalline and amorphous. Means the crystalline means very orderly packing, and amorphous is random packing. So you can observe this by Sachs, which is the technique to characterize the microstructure. And actually, this is the structure represent the brown one is those kind of clusters that starch lie on, and then you have the amylopectin as this greenish line. So with this structure, starch has this strong hydrogen bond between each other, so it's not soluble in water, and actually if you heat it up, it will degrade or it will burn, but it doesn't show any melting. So this is one of the reasons that it's a little difficult to make starch for the products in daily life as plastics. This slide I want to show you, actually people try to make use of starch. We call mealable starch. Mealable means melting, melt it. Because if you want to change the material to change the resource to material, you need to melt or you need to dissolve. So starch is not soluble in water or more solvent. So that's why we need to make it becomes mealable. So one thing is to heat it up with water so you can have this kind of the glue, or you can even make the bread or those kind of shell for drug tablet. And actually, if you add with the plasticizer, you can have this kind of we call thermoplastic starch, which I show you later on. But thermoplastic starch plays a lot of involvement in our daily life. In 1980s, 1990s, people used TPS thermoplastic starch to blend with polyethylene to make the film, and people say that is the film biodegradable film, but actually it's not biodegradable. And but anyway, at that time, people believed that starch is one thing that can help the environment. But currently we have the biopolyester. So we have biopolyester which is biodegradable. So TPS biopolyester becomes again popular in terms of the material that is environmentally friendly. And the starch, when you use it for a while, becomes retrograde, means the packing start again and phase separated. So that's why the product from TPS is not that long. Okay, so let me show you a bit about how we have the plastics that shifted from petrol-based to bio-based. Actually, in our daily life, you may get used to this kind of either polypropylene, polyethylene, polystyrene, and well, the advantages is it's practical. Is function, and you can have a kind of various type of structure, various applications, and especially at low cost. But the fact that, as you may know, is non-biodegradable, it causes the microplastic, and we rarely have the recycle because it's cheap. So that's why it becomes problems at the moment. At the same time, since 1990s, people start to recognize about the biodegradable. So at the moment, we have polylactic acid, which is very popular, biodegradable polyester. And we also have other polyester, including starch, where starch is not polyester. But as I mentioned here, the advantages of this kind of thing is biodegradable, sustainable, and also it comes from renewable resource. Especially starch, if you look at starch, I want to emphasize that starch is naturally available. It means that you can cultivate starch directly from plants, and actually it's ready to be used. You don't need to have fermentation process to change lactic acid to be polylactic or even polyhydroxyocanoate. And starch has its own diverse applications and of course the cheap price. Let me show you what I mean in the title, polymer-based approach. So this is the way that when we have polymer chain, long chain molecules. We have two choices to make it becomes material. One thing we call thermoplastic, which it comes from the semi-crystalline, which is the orderly packing and randomly packing. So this kind of semi-crystalline can give us the material, either film or other bulk materials. Another type of material we call thermoset. Thermoset, as I written here, it cross-link with each other, and you can have helmet, you can have melamine dish, or you can have the phenolic, the circuit board. So with this kind of approaches, you can change materials, polymer resource to be material. So polymer-based approach for making starch to be thermoplastic. So the fact that we want to have thermoplastic, as I mentioned in the last slide, so how can we make it? This is the way that people know for long years that if you have starch, you add plasticizer, you just screw it in the screw extruder, and then you can have this kind of granule or resin we call thermoplastic starch. And inside the structure is something like this. You have the plasticizer penetrate in between the starch structure. So that's why melting can be achieved. So to tell you in details, the know-how of making thermoplastic starch is you can have either water, glycerol, this kind of structure, sorbitol, urea as the plasticizer, just blend it and heat it up and screw it, and then you can have the resin. So with this background, so people use TPS. Yeah, so if you check the website, well, many, including Japanese company, Curare, and also Italy, US, UK, Austria, and Germany. So a lot of the starch or TPS-based plastic are now available in the market, and That's why I'm saying revisiting starch, because starch becomes valuable and becomes practical again. Starch can be thermoplastics. So my question is, then starch can be thermoset or not? As I mentioned in the previous slide, that the structure are different. If you want to have thermoset, you have to have this kind of cross-link structure. But story is not that simple. This is an example of thermoset material when you want to have the melamine dish. So you have the monomer, for example, formaldehyde or melamine cross-linker, and then you blend it, and then you let it melt. So after melt, you press it to form the shape. So with the pressure and the melting and the cross-link happen, three things happen: melting, and cross-link and shaping and become solidified as the melamine. So this is a short slide. So this is a kind of way of preparing melamine dish. You put in the mold first, and then you heat it up, and then you melt it. So this process, you melt it. And then after that, you have this melt, and you put into the mold, and you compress it. Now becomes a bowl. So you can have this kind of bowl very easy from this kind of thing. So how can we have this with the starch? But first of all, we need to recognize the requirements of making thermoset. There are three things. You have to mix the monomer, you have to have cross-linker, you have pre-polymer form, and then you have the full cross-ring or full curing. So with this step that I showed you in the previous slide, requirement number one is meltable. Number two is flowable. Number three is cross-linkable. So starch can be like that. Actually, making starch to be like that is not easy. So this is what I have in mind. So our idea is, first, we modify the starch with some molecules that can make starch to be cross-linkable, thermoplastic starch. Thermoplastic means meltable, flowable. So we have meltable, flowable process. And then you have another molecule to make it cross-link. Then you can have cross-link. So with this requirement number one, number two, meltable, flowable. Requirement number three is cross-linkable. So let's see how can achieve that. I will skip the details of the reaction, but just to tell you that this is the way we call molecular design. So we have the starch and we link with this molecule so that it becomes meltable and flowable. In similar to plasticizer, so we have meltable, flowable, and then we blend it to make TPS, thermoplastic starch, but not just TPS, it is cross-linkable TPS. So this is the schematic just to show you the starch and with some reactive group. So then this is schematic to show you the glycerol, which is meltable and flowable, and this is the schematic to show the overall structure, cross-linkable. So let's see, first is the concept. Second is the modifying starch. So this is the way I modify starch with this molecule and the evidence from the chemical structure analysis. So just to show you that we confirm this structure. So we have the glycerol, which is the plasticizer for starch. We did the same thing. So we modify it and then we characterize it. So we achieve two things. Then we have this and we have this. So we compound or blend this. So it becomes cross-linkable TPS. And then we add this cross-linker. So this is the way we have powder of these three. And then we put into the hot oil bath to melt it, meltable, flowable. And you can see that it becomes meltable, flowable. And later on, it becomes cross-linkable because of this molecule. So it's cross-linked. And then we take it out from this vial, and it looks like this. And that is the thermoset TPS. So my question is, can we make the TPS like melamine? So this is what we did. So we have this, and we prepared it as a sheet, like this video. So we have this kind of thing, and we just melt it and press it, like we press the melamine dish. So we press it, and we put the glass and press it for a while. And after 10 minutes, we have this kind of sheet. And then we have the mold. And then we put on the mold, and then we put it and become tray. So this tray, can you click this? This tray is not water. So you see that we drop the water, is not water absorption anymore. And also oil, not oil absorption. This means that this tray, well, is a kind of prototype showing you that we have some plate that is practical for either the water-based or oil-based. So the conclusion of my talk, I show you that we can revisit starch by having this kind of thermoplastic starch. And actually it was successfully prepared and commercialized by several companies. And at the same time, what I'd like to deliver today is about how we can change starch to be thermosetting TPS. So in the next future, we may have this kind of food container, single-use TPS base that you can throw away after use without pollution. So I'd like to acknowledge the National Research Council of Thailand and Center of Excellence Advanced Material B2ACE, which are supported by Chulalongkorn University. Thank you very much for your kind attention.
Thank you very much for the inspiring and also insightful sessions. I'm actually very impressed by the knowledge and also how enthusiastic you are during the presentation. So thank you for sharing with us today.
Good afternoon again. So welcome back to our special CU Asahi Glass Foundation Seminar 2025. The topic of our seminar is on the advanced material and engineering for societal impact. So this is a great time for us to have the, let's say, the awardee of previous year. So the one who get this grant, very honorable grant from Asahi Glass Foundation. So it will be the good time for them to present their update of their research finding from the previous year. And I would like to introduce myself and also my co-chairman. Okay, my name is Sutichai Assa Bamrungrat from Chulalongkorn University, Faculty of Engineering. Actually, my expertise is on chemical engineering. And our co-chairman, please introduce yourself.
Thank you very much, Professor Sutichai. My name is Natha Thongjun from the Institute of Biotechnology and Genetic Engineering. My expertise is on fermentation process development and scale-up. Thank you very much.
Okay, thank you. So, thank you. So in this session, we will have 6 presenters, the former recipient from Asahi Glass Foundation. I would like to introduce the first speaker. The first speaker is Dr. Nipapan Lucha, and her topic of presentation is on the enzyme incorporated nanomaterial-based potentiometric biosensor for urea detection in clinical diagnostic and environmental monitoring. Dr. Nipapan is from Metallurgy and Material Science Research Institute. So please welcome Dr. Nipapan.
Hi, good afternoon, everyone. My name is Nipapan Lucha, and this is my topic today. Okay, firstly, I would like to introduce about what is urea and why we want to detect the urea. Urea is a key metabolic waste product formed through the nitrogen metabolism. Monitoring the urea level is critical for diagnosis kidney-related conditions. Urea level may vary by the sample metrics such as in the blood, urea, sweat, or saliva. The level of urea will vary from the metric of the sample. Abnormally high urea level may indicate the kidney disease or dehydration, while low level of urea may indicate the overhydration. Currently, the urea is commonly detected via the chromatography, fluorometry, calorimetry, and spectroscopy. These techniques are quite accurate. However, there are some limitations, such as the low sensitivity, high cost, and complex equipment leading to incompatible with the point of care diagnosis. This limitation motivates the need of compact affordable and user-friendly for urea detection. Electrochemical method, particularly potentiometry, offer an attractive feature due to its rapid and label-free detection, miniaturization, compatibility with the body fluid, cost-effectiveness, and ease of use. The direct detection method for urea using the electrochemical technique suffer from the poor sensitivity and poor selectivity. Therefore, we focus on the indirect method to detect urea, where the urease enzymatically hydrolyze the urea to the form of ammonium ion, which are measured using the potentiometric ammonium ion sensor. Potentiometric sensor work by measuring the potential difference between the ion selective electrode and the stable reference electrode. Recent advance in the potentiometric sensor allow the miniaturization and fully integration on the flexible and or paper-based sensor substrate. This device requires the low volume of sample and offer the fast response time. Around just 1 minute, we can detect the ammonium ion and are scalable for the mass production, essential for the variable diagnosis. Here is the mechanism for the indirect detection of urea using the enzymatic reaction. The urease enzyme will convert the urea into the ammonium ion form in the presence of water, and we can detect the ammonium ion by using the ion selective membrane on the ion selective electrode, and we can measure the potential difference in the concentration of urea. This resulting voltage change is recorded and reflects urea concentration. This indirect method allow high selectivity and avoid interference from the other species. And why we have to use the nanoparticle for immobilize the enzyme before detecting the urea? Because we want to enhance the sensor performance, we employ the nanoparticle with the enzyme instead of the conventional enzymatic assay. Compared to the bulk urease, nano enzyme offer the high surface area and faster catalytic activity, and improve the stability and sensitivity, better integration into the miniaturization platform. This makes nano-urease ideal for the portable and real-time biosensing. In this work, we use the urease enzyme to incorporate with the nanoparticle of the polymeric nanoparticle to improve their stability. And the objective of our research are to develop the potentiometric sensor using the laser-induced graphene based on the ion selective electrode for the detection of urea, and to apply this sensor for the determination of urea in the real sample such as human urine. Our sensor was fabricated on the laminated PVC, polyvinyl chloride, and polyamide substrate, and we use the skin printing method to fabricate the reference electrode by using the silver chloride ink, and then we stabilize the reference electrode using the potassium chloride solution, and then we cover with the reference membrane. For the ion selective electrode, we prepare by using the carbon dioxide laser engraving method to generate the electrode like a graphene-like structure on the polymer substrate. And this electrode we use as an ion selective electrode, and we coated with the ion selective membrane that recognize to the ammonium ion, and then we coat with the urease enzyme for the they are for the detection for selective detection of urea. And when we want to detect the urea, we drop the sample on the electrode area here and we incubate and we can detect and measure the potential difference within 5 minutes. And this slide shows the result from the reference electrode that we optimize. In our system of reference electrode, we test by measuring the potassium chloride with the different concentration from 10 power minus 7 molar to 1 molar. And you can see that the signal is quite stable. When we change the concentration of potassium chloride, the signal is stable here and a little bit dip on the potential with the high concentration of potassium chloride. This system might be good to use with for the potentiometric ion sensor. For the ion selective electrode, we try to optimize the thickness of the membrane that recognize to the ammonium ion by vary from 3 to 15 layer. We found that the 10 layer provide the best performance for the ammonium ion detection with the sensitivity around 58.5 millivolt per decade. That related to the theoretical of Nernst equation around 59.2 millivolt per decade. And we can detect with the wide concentration range of ammonium ion from 1 micromolar to 1 molar. And after that, we combine two electrodes that we optimize together and use as a portable ammonium potentiometric sensor for urea detection. And firstly, we try to detect with the ammonium solution. When we change the concentration of ammonium solution, we can detect the potential change with the concentration of the ammonium, and the sensitivity is quite very good. It's very near with the theoretical of Nernst equation. When we want to detect the urea, we test with and without the urease enzyme, and we see that without the urease enzyme cannot detect the urea, and when we add the urease enzyme on the electrode surface, we can detect the urea. But however, the sensitivity is still very low. It's around 15 millivolt per decade. Therefore, we enhance the sensitivity of electrode by incorporating with the nano-urease enzyme that we synthesize. And it was found that the sensitivity was improved by 2 times. Therefore, this is a promising system to detect the urea. With the higher sensitivity, wider detection range from 1 micromolar to 1 molar, and with the low limit of detection. And however, in the conclusion, we successfully to develop the portable potentiometric biosensor for urea detection, and the sensor show the good linearity for urea detection. However, the sensitivity is still lower than the when comparing with the theoretical. This is just the preliminary testing the nano-urease enzyme. Therefore, it might be need to characterize more and optimize the amount and concentration of nano-urease enzyme to improve the sensor sensitivity. And thank you.
For your nice talk. Okay, so I think we have about 5 minutes for question and comments. Any comments from the floor? Don't hesitate to raise your hand. So in the meantime, maybe if you have any question, Ajahn Natha.
Okay, all right. When you mentioned about the detection range, I am not sure. Like you said that you already have the detection range. Would it be possible to compare that with the real sample? I mean, for the urine sample, what do we need I'm not sure if we need any pre-treatment of the urine sample before we can use your sensor.
Yes, this sensor we have already tested in the real sample with the urine sample, and the linearity of the sensor is covered with the range in the of urea in the urine sample. In this case, we can directly drop the urea without any pre-treatment.
Okay, can you make some comparison with the conventional method for measuring urea? A conventional method.
Yes, we compare with the we got the sample from the hospital and we compare with the validate with the hospital results.
What is the benefit? For example, is much cheaper or much faster?
This device compared with the conventional validate method is, I think, is quite very fast because we can detect within the 5 minutes, and I think we can reduce the time for detect to lower than 5 minutes, and the cost is quite cheaper than when compared with the validation method. Yeah.
Thank you very much. I think it's very meaningful research. My question is, what challenges remain before it can be used in practical application? My concern is what is the reliability or accuracy or repeatability for longer time?
In the part of repeatability, in this sensor we can reuse due to the property of the enzyme is can reusable, and but I did not test the repeatability yet, but in normally it can be reusable. Therefore, I think it might be reduce the cost of the sensor, and for the stability, you mean stability? Yes, in this case we cooperate with the polymer nanoparticle, and we think that it should be stable than when comparing with the pure enzymes.
I think that actually it is the accuracy and precision of your sensor.
Yes, the accuracy and the precision of the sensor. For now we just test in the real sample just 1 or 2 sample, and we did not we will further study for the accuracy and precision for the next study. Thank you.
Okay, so do you have any plan for the real application?
Yes.
So when? Maybe next year? Or you
no,
want?
No, maybe it's next 2 months or.
Okay, that's good. Yeah. Do you need any more funding? Don't hesitate to say so now. Okay, any more question? Okay, please.
Hi, you shown a page about the laser-induced graphite. So it comes from the conversion of the polyimide film.
Yes.
Okay, thank you.
Thank you for the presentation, and I have one question. So this is a very, very simple question. So can it recognize urea from the other amide compound? I'm interested in another application.
Possible use for another application, because your method is can differentiate urea from other amide sample. Can we use that for other application?
Yes, in this electrode can apply for other application for the ammonium ion detection, but in this case we just focus on the urea by immobilize the selective enzyme for the urea, but we can apply for any application in the environmental sample or anything that we need to detect the ammonium ion.
Okay, I see. Thank you.
So please thank Dr. Nipapan again for her excellent talk. Thank you very much. So now let's move to our next speaker, Associate Professor Dr. Nat Leelawat from Department of Industrial Engineering, Faculty of Engineering. Today he will talk about tsunami evacuation behavioral study with virtual reality and disaster education to development. Please welcome Dr. Nat.
Okay, good afternoon, ladies and gentlemen. 皆様こんにちは。สวัสดีครับ I'm Nat Leelawat. I'm from Department of Industrial Engineering, Faculty of Engineering, จุฬาลงกรณ์ University. Also, I'm serving as the head of the Center of Excellence in Disaster and Risk Management Information Systems. Also, I'm now the guest professor at Keio University in Japan. First of all, I would like to thank Asahi Glass Foundation that makes my research come true. I have to say that I start the idea of this research in when my Center of Excellence was the research unit. And I spent 2 years during this fund in order to make the idea that we talk within our team and colleagues to make it happen. Next slide, please. Okay, so for the agenda today, I'm going to give you some background about the idea of tsunami evacuation, then my research objective, then some key results that we found from our works in both academic way and practical ways. And after that, I will show you the part of our VR simulation, then our achievement that we published and listed at the end of the projects and summary. Next slide, please. Okay, first of all, the background. I would like to say that when Thailand experienced tsunami in 2004, I still was an undergrad student at that time, and honestly speaking, I did not know about tsunami at all at that time. I even don't know the term tsunami. Then it's first time in my life to hear the term from the news that, oh, tsunami is the huge wave that caused by the earthquakes. And starting from that, I think, I believe that many people in Thailand, maybe my age or people near my age should know about tsunamis. And I expect that everyone in Thailand should know. But then, when I start to teach some students, the generation gaps occurs. Many students told me that they never experienced tsunami because in their life there was no tsunami since they were born because they were younger than 20 years old, right? So last year it was 20 years after the 2004 tsunamis. And we arranged many activities in Phuket and Phang Nga area. And at that time it was my motivation that I have to do something. Otherwise, the young generation, they will have less awareness and less awareness in the futures. But we cannot create tsunami to let them experience. So what we can do is make the immersive solution like the virtual realities in order to let them experience some things, in order to try some things. Not the real one, but somehow they can feel like they are a part of it. Okay, and tsunamis is the major disaster that, of course, the frequency is very low, but impact is very high. I believe that many professors from Japan, you know well better than me about tsunamis. And this is the reason that we have to work and consult many professors in Japan in order to learn a lot, especially about bosaichi, because we don't have bosaichi in Thailand. And that's why we need to know how the disaster prevention established and continues, and why people, especially the elementary school students, still learn about it. Okay, so that is the part of our motivation, and we also think that once we have the effective, that was my assumption. I thought that once we have the effective warning system for tsunami, it should save a lot of life. But then we conducted a survey. Our preliminary survey found the different things. We found that many people answers to us, even they heard the tsunami warnings, they may not evacuate. Why? Oh, that is the reason that we start to find out the factors that can influence the tsunami evacuation. At first I also guessed probably maybe they thought it's just a drill or the false alarm or whatever things, right? But we found some insights from this research. Next slide, please. Okay, so we have two objectives for our work. The first one, I want to identify which one is a real factor that can influence the people to evacuate once tsunami happened. Okay, and we did a lot of literary reviews. We tried to find some theory like the protection motivation theories to find out what exactly the social factor that can make one person thinks that we should evacuate. Okay, let me interact something with you right now. Let's say, of course, we don't have tsunami here, right? But let's say if we will hear the fire alarm in 1 minute later, who is going to evacuate from this room? Please raise your hand. Anyone? Okay, some of you. Who will just continue sitting and listen to me? Maybe even me, I will run out of this room too, right? And who will just look around to see your friend on the right-hand side and left-hand side and follow that action? Yeah, some of you, right? Yeah, we found that because not everyone will be the active evacuators. Of course, if you are active evacuators, you will be the one who can save your life. But if you are the second group and the third group, it depends on your luck, right? We cannot make sure that you can evacuate or not. That's why we try to find more theoretical factors that can interpret this kind of theories and can interpret in the term of tsunami in Thailand. And the second objective, we want to develop some educational tools that can teach the young generations about evacuation once tsunami happens, and we choose virtual reality to be our tools. Next slide, please. Okay, so this is our proposed model. We follow the applied theory of the PMT, and we found that once people want to evacuate from whatever things, they will consider two factors. First, they are the threat appraisal and coping appraisals. Yeah, those two. But when we want to know which one can influence the threat appraisal and the coping appraisals, we need to find out some potential factors, and we choose these three. First is the gender, second is age, and the last one is the past tsunami experience. And once we say past tsunami experience, and if it's in Thailand, of course, we have to exclude the younger than 20 years old sample out, because of course they will not have any tsunami experience in Thailand. Okay, so our sample start from at least as 21 years old until more than 60 years old. And we try to separate people into three groups, because we believe that the different group of people should act different ways. Our group consists of the first one, the local people. Local people mean the one who live, stay, work in Phuket and Phang Nga areas in Thailand. And the second group is the non-local workers, like the expat or someone who come from other hometown to work in Phuket and Phang Nga zones. And the last one is visitors or the tourists who just come for travel or short-term visits or whatever things. Okay, so we found the result like this. The solid line indicate the significant effects, right? So you can see that gender and age are the two significant effects that can add more threat appraisals. And we found that both threat appraisal and the coping appraisal also can positively influence the tsunami evacuation intention, which at the end of them will influence the tsunami evacuation action selection. And yeah, we learned something from those insights. For example, can you guess between men and male and females, which one have higher awareness in terms of tsunami disaster? Females, correct? Yeah, and it's also in line with the theory that normally female will have high awareness for the risks. Okay. Then next slide, please. Okay, another objective, the second one, we want to let the kids try something about tsunami evacuation, and we want to learn some behavioral action from their decision makings. So we developed the VR tools, and we put the model of Patong Beach in Phuket into our VR models, and we develop some scenes. And all the scenes, actually, the answers are correct, but we just want them to choose and tell us the reasons. For example, the first scene, we let them choose between going to the family members first or evacuate first. Of course, it's fine because we don't know the result at the end, right? They can choose, but after they make decision, they have to tell us why they choose like that. Okay, the second scene is the route between the one that have evacuation sign and the one without evacuation signs, and also the one with the hazard zone and without the signals, signage of the hazard zone. Next slide, please. Okay, this one will show some simulation video that we took a part of our evacuation in VR to show off, or maybe we can just skip and show that if we still have time. Let me talk about the achievements of these projects. Okay, we published one journal articles to show about those identified factors. from the sample that we found in sustainability journals. And also, next slide please. We also submit our work to join the 9th International Innovation Invention Competition in Canada, and we won the Gold Award and 2 special awards from those VR tools. On the right hand side, you can see that is our VR tool that we put on the showcase in the Thailand Inventors Day last year. And the left hand side is not only for academics and competition that we join, we want this kind of knowledge to go to ordinary people and public. So we published one white paper in Thai language about the factor that can influence people evacuations. Next slide, please. So in summary, we identify key factors, we develop the evidence-based evacuation model, and we create the 3D VR models. So this is all from me. Thank you so much, everyone.
Thank you very much for the excellent talk. So I'm not sure if you have any question for our second speaker. Please raise your hand if you have any question.
First of all, I would like to say that I agree with you that females always has a better sense than our male, in everything. Okay. So in your study, let's say, I heard recently that for the Andaman, recently it is becoming active again. So do you have any suggestion for Thai people?
Okay, actually this one will be somehow, I want to talk in terms of not geology, but in terms of the warnings and the engineers terms. I think because of the 2025 Mandalay Myanmar earthquakes, so it's pushed a lot for the current warning system in the countries, right? As you know that on 28 March this year, right, we experienced the earthquake even in Bangkok, and at that time, I think many of you got the warning system through SMS delay, right? Delay, even someone got delayed for a few days. That's why the government tried to push a lot for making it the cell broadcast like in Japan. Yeah, so we expect that if there is anything happen in Thailand, we can get the cell broadcast. But come back to the story about Andaman zones. If the trigger of the earthquake epicenter still at the same area of the 2004, based on the study, we have about 90 minutes before it's arrived the country. So we hope that we can have time for evacuations, but we cannot reduce our awareness because of course, not only the RJ area that can create the tsunami, we also have to be aware for other parts near Myanmar as well.
Thank you for the presentation, and I want to ask you about have you observed any difference in the understanding or the response before, such as between the children and the elder age?
Okay, thank you so much. Yeah, we found the different, but in terms of correlations, we found something interesting. Can you go back to the model slide, please? Yeah, among all, right, the one that we found between age and the trace apostle is not positive correlation, but it's negative association. So it means the higher age, the less trace apostles. So this is what we found. It's quite surprised. We always expect that older people will be better in terms of assessing the risks and threats, right? But somehow it seems like the older, the less of those kind of awareness we found.
And this is the study from Thai?
Yes, from Thailand.
And how about another country? The same?
In other countries, they did not use the exact same factor as us. Yeah, what they use is the threat and coping, what they put some different X parameters. Yeah, but we want to try to understand the age, if they have any correlation, that's why we put age here.
I have a similar question as my colleague here. What other observation surprised you? Do you have more to share?
Okay, thank you so much. Okay, in addition to that we found, it's about past tsunami experience. Actually, this is what we expect, that it should be solid line. It should be significant potential factor, but it's not. You can see the bottom left, right? It's insignificant. So actually, people who have or who don't have past tsunami experience, does not contribute to any awareness. for significant factors.
Okay, this means people who have experienced tsunami before, they will ignore the second one.
I would say that the behavior of both the one who experienced and not experienced behave quite similar. Yeah, so it's not significant difference.
Thank you.
Thank you. Any more question? Okay, if not, let's thank the second speaker again.
Thank you so much. ありがとうございました。
Okay, thank you. So now I would like to introduce the third speaker. The third speaker is Assistant Professor Chayut Ngam Khanong. He is from Department of Civil Engineering, and today he will share us on the topic a circular economy approach to eco-friendly and environmentally recycled concrete sleepers. So please welcome อาจารย์ชยุทธ
Thank you very much for the introduction and good afternoon everyone. My name is Chayut. I'm from the Department of Civil Engineering, Chulalongkorn University, and I'm now the head of Advanced Railway Infrastructure Innovation and System Engineering Research Unit here at Chula. And my topic today is about the circular economy approach to eco-friendly and environmentally recycled concrete sleepers. So let me introduce. I split my contents into 5. So I'll start with the introductions about the C&D waste management, Thailand railway research expansion, ballast track and circular flow process, material and mixed proportion for concrete, results and conclusions. So let me start with the background. So in Thailand we have got lots of demolish, for example, from the buildings, from the old infrastructure, from the bridge, from the railway track. So we generally we generate more than 1 million tons a year for the concrete waste, and most of them has been used for landfills instead of being recycled or reused. So we try to reduce the waste from the demolition of concrete. So to reduce the need for natural resource. My apologies is Thai, but this is the slide from the Department of Rail Transport, from the Ministry of Transport. So they show us this is the expansion plan for the rail infrastructure development. So at the moment, we have about 4,000 single track, and in the future we try to double all the track. It means that we need a double of materials used for building or for constructing the railway track. So it will be 5,000 tracks with the double, so it means more than 10,000. And we also, this is the high-speed rail plan, so we're trying to build the high-speed rail across the country. So at the moment we have this line from Bangkok to the Nakhon Ratchasima under construction, and we try to expand it into Laos, and we can go to China in the near future, and we plan to build another line to the north and another line to the south as well. So that's the plan of our development plan of the rail infrastructure. And I just want to briefly introduce what we are constructing. So in Thailand for the double track railway projects, so it's called ballast track. Ballast means the rock aggregate, rock here underneath the track. So in terms of the track components, we have rail pads, fastening system, sleepers, ballast, sub-ballast and subgrade, which is the compaction soil underneath it. So what we are looking at is the railway sleepers, which usually made of concrete. In the past we used wooden timber for it, but nowadays we use concrete sleeper for this. It means that in the near future we need lots of tons of concrete, million tons of concrete to build infrastructure. I want to show you the number. So the spacing of the concrete sleepers is about 60 centimeters, and imagine 1 kilometer we need 1,600 concrete sleepers, And if we have 5,000 kilometers, so we need about 16 millions concrete sleepers. So, and the volumes of concrete is about 0.3 cubic meters. So we need in total, for the projects, we need about almost 5 million. So we found the opportunities. So why don't we use the waste? Because there's a life cycle. There's a life cycle of concrete, so we can reuse it from other infrastructure as well. Or we have the concrete sleeper that has been dumped across the railway line. If we go to the existing site, you can see a lot of concrete sleeper has been dumped across the track. So we found some opportunity to do it. So we try to reuse it, recycle and reuse it. And so it can, because majority of them has been used for landfill or it just dumped along the track. So and we found that if we use recycled concrete aggregate from random sources, there will be some inconsistency in terms of material properties. So we try to get the properties from the concrete and rebuild the new concrete. So I want to show you about the circular back once. Yes, this is the circular flow process. So this is what we do in the lab here. So we start from getting the out of service railway sleepers, and then we send all of it to the crushing plant for the recycle plant from Bangkok Metropolitans. And then we collect it, and then we try to do some collection classification in our lab. And we test all the properties in our lab, and then we try to build a concrete. This on the left hand side is just the lab scale. But if you want to expand it into the full scale or to build a new one, so we need on the right side, so it's a manufacture of the concrete. We use it in service and end of life, and then we can reuse it again. What we are doing now is to use the end of life concrete sleepers and build a new one here, but unfortunately we can do only in lab scale at the moment. Next please. So this is the out of service railway sleepers that we get from the Italian Thai company and State Railway of Thailand. So we go and collect them. And next slide please. And then we send it to the crushing plant in the Onut area. So we collaborate with the environment department from Bangkok. And then we adapt we got the lots of aggregate, but the size is mixed. Sometimes it's big, sometimes it's small. So we need to recrush it. We need to classify it in our lab. So we use we got it from the the rice for the machine for how to say classifying rice in Thailand. So we got it and adapt it, change the size here to be able to get the proper size for aggregate. And then we got this, and then we test and make a new concrete from here. So in terms of material and mix proportions, here we don't use only the recycled aggregate from sleepers. We also compare it with the random source recycled aggregate. So this is what we got. So it can be from bridge, from building, from everywhere, let's say from everywhere. So when you try to compare the consistency of the properties and the results. Next please. So we try to get all the size first to have the same size of this is a particle size distributions. We try to get the same size. We see it again in our lab, and then we test the material properties of aggregate, and then we decide for to meet the standard of the railway sleepers. Next please. And this is we got these things from the chemical engineering department, a graphene quantum dot, because it's the nano material derived from the graphene. So we try to make it added into the concrete because in the past we have done some work and we found that it can potentially increase the mechanical properties of the CA mortar of the mortar. So we try to add it into our mix as well and compare to the case without GQD. Next, please. This is the mixed proportion that we have. We have the case of natural aggregate. We have the recycle. We have the recycle from random source and concrete sleepers. And we compared also the case with and without GQD. Next, please. So let's see the result. So if you see the result for comparing to natural aggregate concrete from the first one, this is the slump test to see the workability of concrete. If you see collapse, it means that the concrete can flow and it's easy to be used. If you see 40 or you see a number, it means that concrete does not collapse. So it's sometimes when we use in the real side, it's difficult to flow. So as we compare it with the compressive strength, and we see some reduction, of course we see some reduction, we use recycled aggregate, and we try to compensate it by adopt the mixed proportion, and we try to add the proper dosage of GQD. Next, please. And then we test the also fracture strength, again the same as compressive strength. Next, please. And also we test out also the durability, water absorption, porosity, and also chloride ion penetration when it used nearby the beach or the sea to check how the chloride can penetrate. So we found from our work, we found that if we use the concrete sleepers, recycled concrete sleepers, we can also meet the standard of the new concrete sleeper as well, and it's performed better than the random source concrete sleepers. And we also see that GQD can improve mechanical strength of the concrete, and also we see that all mix can meet standard except the 100% natural aggregate concrete from the random source. So we see in the near future we're trying to build the actual recycled concrete sleeper to be used in the fields, and we hope that we can do it. Next slide. So there's a support. Thanks for the support from the Asahi Glass Foundation, and I would like to thank also our company partner, the Crystalline from the chemical engineering, also the Italian Thai development for the support the concrete sleepers. And I like to end up with this railway market. I also invite you to visit this place. It's a very famous place. It's very unique. Yes, thank you very much.
Thank you very much for your nice talk. So, any question from the floor? Yes, please.
Hello. Okay, my question is about how did you get this idea about graphene quantum dot? My impression is that quantum dot is associated to optical research, optical applications. So where did you get this idea about graphene quantum dot in improving the structural durability of concrete? Thank you.
Honestly, it's not my idea. It's my colleague's idea. He used it. He used it in the mortar. He tried the quantum dot in the mortar. It's the mix of the cement, sand, water without the rock, and we're trying to expand it into the real application in the concrete. So he probably, I don't know how he got this idea, because and honestly we are the really first few groups to do this quantum dot into the concrete. Yeah, thank you very much.
Can you make some comment in terms of cost? Would it be good to add quantum dot?
It's at the moment it's very difficult to do a mass production. So it's because you probably know it's not easy to make because to be able to build the real application of infrastructure, it's still very difficult to get very large portion. So at the moment there's no idea that's on course. Yeah, but if you look at our studies, we use only 0.3% in our concrete. So we don't use a lot, but if we want to expand into the real application, that's the time we have to think about it. Thank you very much.
So thank you very much for your talk. So please say thank you to our speaker again. Thank you very much. And now let's move to our next speaker, Dr. Wuttichai Rian Thipayasakul from Department of Material Science, Faculty of Science. He will talk about waste to value transformation of spent alkali battery electrode powders to photocatalyst for organic pollution remediation and green hydrogen production. Please welcome him.
Good afternoon, everyone. I am Wuttichai Rian Thipayasakul from the Department of Material Science, Faculty of Science, Chulalongkorn University. And first of all, I would like to thank the Asahi Glass Foundation to this research for me to work with. And the topic today is about waste to value transformation of the spent alkali battery electrode powders to photocatalysts for organic pollutant remediation and green hydrogen production. And first of all, I would like to remind you guys about what we need to face nowadays globally. We need to, in terms of the energy and environmental issue, we have so many things that we need to face. First of all, one of the most important issue that we have to find a way to solve the problem is the waste management. We have a lot of waste from the industrial part and also agricultural part and also from household and all. Next, we also have the air pollution waste. We need to face the like a PM 2.5 and also water pollution due to the unappropriate wastewater treatment, and also we need to have the global warming issue and also energy crisis. We need to find some renewable energy and also some alternative energy. And let's think about this and let's imagine how great it is if we can find a possible solution that we can solve all these problems together at the same time. And that's why we came up with the idea. Our idea is next please. Our idea is we call the waste to value transformation. We try to do the waste reutilization. We have some industrial and agricultural waste. We consider it as zero things, and because it has no value, and we turn it to be a hero, turn it to be the materials or technology that has ability to solve the environmental issue. And one of the most important and effective approach is the photocatalysis. And next please. The photocatalysis is one of the bio-inspired concept that mimic the natural photosynthesis. They try to mimic the chlorophyll. Chlorophyll act as a catalyst to transform the light energy to chemical energy, and we try to develop some materials that we call photocatalysts that can transform the light energy to accelerate some chemical reactions, and then we can do some water splitting to create the oxygen or hydrogen from water, or we can create some chemicals from the carbon dioxide or carbon monoxide. And this idea discovered by the two Japanese scientists, Professor Fujishima and Professor Honda, 50 years ago, by water splitting of the titanium dioxide by UV irradiation. And next please. And for the photocatalyst, they have some mechanism behind them, and they start with the light absorption, and then the light can excite the electron from the valence band to the conduction band, and then they can create some surface reaction like a reduction reaction or oxidation reaction, and can generate some reactive oxygen species. And for the strategy that we can work with the photocatalyst, there are so many things that we can play with the photocatalyst, including the band gap engineering or doing some surface modification like physically and also chemically, and change some morphology and doing some composite formation or defect engineering, and also loading some co-catalyst with the catalyst that can enhance the photocatalytic activities of performance. And next please. And application of photocatalysts in terms of energy and environment, they can use in the water splitting to create the oxygen and hydrogen used for carbon dioxide reduction as well, and maybe can use in the energy storage system like a semiconductor or battery. And also for environmental impact, they can use in the waste water treatment and also air purification. Next, please. And get back to our idea for our group. We have the idea to transform some industrial waste into the photocatalyst, and we aim to the zinc containing waste because we know that zinc oxide is one of the most effective photocatalysts using nowadays. And for the zinc containing wastes, one of the most used one is the spent alkali battery. Spent alkali battery is the primary battery that used the most around the world, about 80% of all of the primary battery. And after use that, they can go to landfill, and sometimes they create some chemical leaking to the land or some water resources, and that gonna affect our organism in the water or affect the environmental as well. And we try so many ways to turn some electrode in the spent alkali battery into the zinc oxide. Like we try to use the thermal treatment method, precipitation, hydrothermal, and also solution combustion. And once we get the zinc oxide photocatalyst, we can use them as the like a hero to destroy some organic pollutants. And next, please. Let me talk about the spent alkali batteries. First of all, we need to know about their composition. In the spent alkali battery, in the alkali battery, first of all, I would like to mention about the cathode and anode, which is their electrode. At the cathode, the materials that used for the cathode in alkali battery, they start with the manganese dioxide. After they get the reduction reaction, the manganese dioxide turn to the manganese 3 oxide. And on the other side, for the anode oxidation reaction, they start with the zinc metal, and after they got oxidation, zinc metal turns to be zinc oxide. And for the overall reaction, you can see our product is zinc oxide and manganese 3 oxide. And we try to separate the zinc oxide from this spent alkali battery and use it as the precursor for the zinc oxide photocatalyst. And next, please. And for the experimental, we collect all of the spent alkali batteries and then try to dissect them into small pieces and separate them into categories metal pieces and also cathode and anode. And for this project, we try to use the anode, which is the zinc oxide mainly. And once we get the anode powder, we grind with the vibratory mill and wash it so many times and dry it and sieve to do particle sizings. And also we try to develop a new method that we not use chemical at all. In the past, some people try to recover zinc oxide from the spent alkali battery, but they use acid leaching or use some base solution. But we try to do the thermal process that without any chemicals involved, and we try to calcite it in different temperature, and we get we call it anode zinc oxide. And then my student come up with the idea to have something to support the zinc oxide as well, and she recommend us to use the eggshell, which is the bio resource for the calcium carbonate. And the calcium carbonate has been known as the effective adsorbent for organic compounds, and due to their porous structure and also some organic functional groups at the surface. And we try to develop the eggshell supported zinc oxide composite from waste from spent alkali battery and also from the eggshell and with the thermal process without using chemicals. Next, please. And to make the composite, we mix the anode zinc oxide and eggshell and silicate, stir and dry, and also calcite them together at the 400 degrees C, and then we got the composite. And after we got the composite powder, we try to study the photocatalytic activity by the organic dye degradation, and we use methylene blue as the sample of the organic dye. And also we do the UV irradiation under the backlight lamp and for 4 hours, and also collect the sample every 20 minutes and study the photo degradation process. And next please. And we found that next, please. And we for the characterization, and we found the phase is the calcite and zincite. And next. And for the microstructure, we found the eggshell as the substrate for the rod shape and zinc oxide particles. Next. And for the photocatalytic activity, we found that after we add some calcium carbonate onto the zinc oxide, we can enhance their absorption capacity and help to increase the rate of the degradation of the dye. Next, please. And we study about the scavenger to learn about the mechanism of the our photocatalyst, and we found that the whole and hydroxyl radical are the main reactive species for the degradation of the organic dye. And next, please. And we study the stability and reuse stability of the photocatalyst, and we found that they have the high stability and reuse stability for our developed photocatalyst. Next, please. And that's the conclusion of our project, is that we find the facile co-calcination without using chemical method to develop the composite between the waste, two wastes, and they show the excellent performance for the dye removal up to almost 100% and show the high stability and can reuse for more than like 5 times. And we study the mechanism that we found the hydroxyl radical and whole is the main are the main reactive species. And that, I think that is from my project. Thank you.
Thank you very much for your talk. Any question from the audience to our speaker?
Thank you very much for your great presentation. It's very meaningful. And I have a question for you. Could you tell me about your evaluation of cost? Because it's cost not only for sustainable and recycle, but also gathering and dividing and sourcing the material.
For the cost, actually, most of the cost is happen at the process of the calcination, because we need to use the oven, and actually the cost is not that high because the calcination is just only 400 degrees C, and it's just only like 2 or 4 hours. Is not that much, because all of our resource is the waste, so we don't have cost for any chemicals.
I see. So regarding the gathering, is it common for your country to divide such a kind of spent battery or some other materials? So
what do you mean? I'm sorry.
Is it easy for you to gather such a kind of material?
For the spent alkali battery, right? And we have the contact with the what was it called, the Center of Hazardous Materials Waste or something in July, and then they can provide us our raw materials, and also sometimes we contact to the Bangkok. I mean, what's this called? I'm not so sure. The กทม ครับอาจารย์
You mean the Bangkok municipal waste management?
Right? Yes, please. Thank you. And then they can provide our raw materials. Yes.
I got this. Thank you.
Okay. So if there is no question, let's thank our speaker again. Thank you very much.
Okay, so I would like to invite the fifth speaker of today. This is Assistant Professor Dr. Pirapat Thongnuk, and he is from Biomedical Engineering Program, Faculty of Engineering. And today he is going to tell us on the topic of development of strong, tough, and flexible fiber for biomedical application from engineered silk fibrin peptides mimicking molecular architecture of collagen microfibrils. So please welcome อาจารย์ Pirapat.
ขอบคุณครับ So good afternoon and thank you very much for having me here and for the support all along the way with the Asahi grant. And sorry that my title is a little bit longer than the other project. And what I want you to focus on is that I developed the silk fibrin peptides silk fibrin mimicking peptides. And the application of it is initially for biomedical application. I want to have the tough and strong fibers. So the aim of my project is that when we look at the collagen molecules, we all know that it is composed of triple helix, and the advantages of collagen fibers is that they are very strong, they are tough, and they are flexible as they are present in skin, in the bones, so they are very strong and they can receive a lot of cyclic loads. Whereas the disadvantages of collagens are they require complicated extraction, and we also cannot have a lot of them compared to silk, and they are very difficult to handle. They are difficult to mold into different shapes and forms. Whereas when we look at silk fibrin, we can extract it from the cocoon of silkworm. And the secondary structure of the protein in silk fibrin is the beta sheet structures, as you can see from here. So the structure of silk and collagens are different. The collagens, they are triple helix, but the silk, they are beta sheets, crystalline beta sheets. And the advantages of silk fibrin is that they are strong, but they are brittle. Sorry, this is disadvantages. And the good thing about silk is that we can extract silk fibrin from silk cocoon very easily, and we can have a lot of them because it is agriculturally enriched. That's the reason why I want to design silk fibrin to mimic collagen fibers, because the structure of collagen, they are very strong and tough. Maybe if we can design silk to adopt the molecular architecture that are very similar to collagens, maybe we can achieve tough silk fibrin. So when we look at the silk fibers, they consist of two proteins that we call silk fibrin, which is a core, makes up about 70% of the weight. And we also have a sericin, which is another protein that acts as a glue, that glue fibrin together into the fibrin core. So this is the beta sheet structure that stabilizes the silk fibers. So when we have a look at the primary structure of silk fibrin, you can see that in the crystalline domain of silk fibrin, we have the repetition of some of these amino acids, glycine, alanine, glycine, alanine, glycine, and serine. We have the repetition of these amino acids like 6 times or more than 10 times. So these domains are very important for the formation of crystalline beta sheets. So we are interested in the GAGAGS. So we try to play around with the sequence by simulation. You can see that when we have the 4 repeats of GAGAGS, and I am going to call it the silk tag. And we play around with the condition. If we wet spin the 4 repeats of silk tag, we should get something that is similar to this one. But still, this tetramer of the 4 repeats are not very similar to collagen fibers. However, when we have the 4 repeats of silk tag and we start it off with cysteine amino acid, and we have the ending with tyrosine ones, we can have something very similar to triple helix that I showed you before in the collagen. So we want to have the mimicking peptide that have the 4 repetition of GAGAGS, and we want to have cysteine at the start, and we want to have tyrosine in the end. But after the design, we make some order to the company for chemical synthesis of this sequence. The problem is that to have the adequate amount of protein, it is very expensive. So we don't afford to do this. We don't afford to have the proteins by chemical synthesis. So we decided that we would put the sequence in E. coli bacteria, and we want to make the protein from E. coli instead of chemical synthesis. So the picture on the right-hand side is the protein fibers after wet spinning. You can see it here, and when we zoom in, we can see that the fiber is quite nice and beautiful. Okay, so at the moment, we are waiting for the plasmid to come back to our lab, and we want to transform the E. coli with the plasmid, and we want to have the bacteria to produce the protein in the bioreactor. So because of that challenge, we shift the aim of the project a little bit by we want to integrate this silk tag with a protein. And during silk fibrin, like initially we can prepare silk fibrin into a solution. And after waiting a little bit, it will become a hydrogel, as you can see at the top here. So during the gel formation, the silk fibrin solution here will adopt the crystalline beta sheets that stabilizes the hydrogel formation. And we believe that if we have the silk tag, and this tag can interact very strongly with the crystalline beta sheets here, and then it will kind of encapsulate the drug within the crystalline beta sheets here. So we can control the release, or we can prolong the release of the protein here that is conjugated to the silk tag. And the application of this may be for the slow release or sustained delivery of some protein drug. Next, please. Okay, so we try to see that. We try to prove our concept by having E. coli again, and then we put these kind of DNA sequence into the bacteria, and you can see that we have the silk tag at the start, and then we want to track whether the tag can interact with the protein, with the silk or not. So we can, we had the green fluorescent protein after the silk tag so that we can see the fluorescence of this tag. And we purify the protein. Next, please. And then we put it into the silk fibrin solution, and we let it gel a little bit, and then we have a hydrogel block with the silk tag interacting with the crystalline beta sheets, and we can then measure the amount of protein releasing from the hydrogel block. Next, please. Okay, so here we can prove that the rate of delivery or the rate of protein release depends on the length of the tag. So for example, if we have only one repeat of GAGAGS, the release rate is over here. So the slope of the curve is like the rate or the speed of the release. But if we have 7 repeats of GAGAGS, the rate is very slow. Next, please. And then after the proof of concept, we want to conjugate the silk tag with actual growth factor that has some bioactivity. So we conjugated the silk tag with BFGF, and we also have the plan for epithelial growth factor and LIF as well. And then we proved by this gel that we can successfully produce the fibroblast growth factor tagged with silk tag. Next, please. Okay, so our design is that we want to have a hydrogel that continue releasing basic FGF at a very sustained rate, and then the basic FGF can help in wound healing. We proved that the basic FGF, after conjugated with the tag, you can see that the rate of release is very slow at the first 10 days, and then it reaches the same amount of release after 30 days or 1 month, which means that our silk tag can delay the release, but it keeps the final concentration of the drug to the same concentration. And this release is very specific to silk hydrogel because we do the same thing with gelatin hydrogel, and the concentration of the drug released into the buffer is not different between the ones with the tag and the one without the tag. Next, please. Okay. And after conjugation with the FGF, we want to see whether our tag would reduce or would it increase the bioactivity of the FGF. But we can prove from MTT assay that they are all the same, not different. Next, please. And we did in vitro wound healing assays, and you can see that the normal FGF commercial ones, they can promote the wound healing, almost close the wound completely. But our FGF with silk tag or 6R, they heal the wound, but not as good as the untagged one, the commercial one in vitro. So then we move to our in vivo experiment. Please, next slide, please. Okay, and you can see that this one is the commercial one, and this one is our FGF with the silk tag, and in the end, they can heal the wound with minimal scar. Next, please. Okay. So the conclusion is that we can produce the biomimetic peptide conjugation that retains the BFGF functions, and the BFGF with silk tag gives a faster rate of healing in rats, although they give slower healing rate in vitro. And this should provide some economic impact on silk industry, especially in Thai silk industry. And the conjugated growth factor production is scalable as well because we can do the E. coli culture in bioreactor. Next, please. Okay, and with the support of Asahi Glass Foundation and Chulalongkorn University, this is what we can produce. We can produce a research article, and we can produce a review, and we also can produce a petty patent. Next, please. I would like to thank Assistant Professor Kittikun Wangkanon from Faculty of Science as well for helping me with the production of the recombinant protein, and Dr. Juthatip Manitsorn, Dr. Chaturong Promsuk, and Professor, Assistant Professor Sarawut Labmani for animal testing. Thank you.
Thank you very much for your nice talk. So, times for comments and question. Maybe another word, yeah. Biomedical engineering, quite difficult. So please.
Okay, thank you for your presentation. Regarding to the mass production, so what are your main technical or the economic the challenge in the scale up the production of these silk fabrication, the silk the fibrin, the fiber.
Okay, thank you for the question. So the main challenge is that even though we can design the DNA and we can design the protein primary sequence, however, as you can see that the sequence consists of the repetition of G and A, G and A, G and S, and this pose a challenge in production as well because they are mainly hydrophobic, and E. coli bacteria, they don't like to produce very much hydrophobic proteins. So we have to, play around with the production system as well. So maybe that's why by fusion with the hydrophilic protein, it improves the scalability of the production as well.
So if not, let's thank our speaker again for his excellent talk. Thank you very much. And now let's move to our last speaker of the day, Dr. Abdul Hadi Yaakob from Institute of Biotechnology and Genetic Engineering. Today he will talk about advanced electrochemical DNA biosensor for monkeypox virus detection. Please welcome Dr. Hadi.
So good afternoon, everyone. My name is Dr. Abdul Hadi Yaakob, and I'm from Institute of Biotechnology and Genetic Engineering. And today's topic is advanced electrochemical DNA biosensor for monkeypox virus detection. Monkeypox or mpox is a viral zoonotic disease caused by the monkeypox virus, and which belongs to the orthopox virus genus. And it can be classified into two primary clades, which are clade 1 and clade 2. And in 2022, the World Health Organization recognized its global spread and declared a public health emergency of international concern, or PHEIC, involving with the clade 2. And as of last year, the clade 1 emerged and prompting the WHO to redeclare it as a PHEIC again because of its higher mortality rate and also a more severe symptom. And as with other viral infection, the polymerase chain reaction, or PCR, is the gold standard method for diagnosing mpox virus. And PCR is highly regarded for its high precision and also high sensitivity. However, the technique itself poses some challenge, such as cost, processing time, and also limit availability, especially in remote setting area. And as of last year, no rapid antigen test kit has received an emergency use authorization, and leaving only PCR primary option. And as we look ahead, an alternative molecular biosensor are clearly needed to address this limitation effectively. And various biosensors have been explored, such as the colorimetric DNA sensor, the fluorescence DNA sensor, and however, the electrochemical DNA sensor, even though it was widely adopted in various biosensors, but there is no report on electrochemical DNA sensor for mpox virus. And this gap motivates us for the development of an electrochemical DNA sensor. And most electrochemical DNA sensor falls into two categories, which are labeling or label-based with the label-free. For the label-based, it involves the use of molecular tagging, such as enzyme, nanomaterial, or even redox molecules. So it means that in the presence of the target DNA, it will trigger the electrochemical response. And this is what we call signal on. And while sensitive, it can be cumbersome and time-consuming to prepare. And conversely, for the label-free, it involves the use of the metal-based redox indicator to indirectly monitor the presence of target DNA. It means that in the presence of the target DNA, it will suppress the electrochemical response. And this is what we call signal off. Why it's simple and easy to use, it has limited sensitivity and inconsistent control measurement, and also the counterintuitive analytical outcomes where high concentration of the target DNA will result in a low electrochemical signal. And with this limitation, it led us to the development of a PCR-free, label-free, and yet signal-on. And it started by the DNA probe, the purple one here, that carrying a single base mismatch by replacing guanine with cytosine to mimic a natural base mutation. And then there's when the target DNA come hybridized with the DNA probe. As you can see in the yellow line, it forms, create a binding pocket for the silver, as you can see here. And silver can bind at this available site through the formation of the nanocomplex, this one. And this nanocomplex serves as a redox center for the electrochemical detection, and which it gives a strong signal on, as you can see here in this graph. And for the sensor fabrication, it concludes a three simple steps. Sorry for the animation. It concludes three main steps, which is the first one is the production of the screen print electrode. And then the second one is the gold electrode deposition, which serves as electrode modifier and also an immobilization substrate for the DNA probe. And then the last step is the DNA probe immobilization. And for the results and discussion for this talk today, it will be divided into four parts, which are characterization, analytical performance, NFC integration, and also the sample analysis. So for the characterization, we initially studied the characterization using morphological characterization using SEM and also laser confocal microscope. And from this result, as you can see here, it confirmed the successful production of the gold nanoparticle and also the successful immobilization of the DNA probe on the electrode surface. And we further corroborate this immobilization using the electrochemical technique. And it clearly confirmed the successful immobilization and also the successful hybridization with the target DNA. And from this result, it was estimated that the DNA surface coverage was estimated to be 2.12 times 10 to the 11 molecules. And next, we further study the analytical performance. And we study using two electrochemical techniques, which is the cyclic voltammetry in the first one, in the figure A, and the amperometry in the figure B. And we observed that the peak current is increased with increasing DNA concentration, as you can see here. And the similar result was also observed with amperometry. And for the cyclic voltammetry, the linear dynamic range was established up to 10 to the 6 picomolar with an LOD of 1.8 picomolar. And for amperometry, the linear dynamic range was established up to 10 to the 4 picomolar with the LOD of 2.08 picomolar. And we further study the selectivity with various pathogenic species, as you can see in figure C. Interestingly, this sensor is specific to Oli, monkeypox virus. And also, it can be used to detect the monkeypox virus with G2C based alteration as well. And we further transform this sensor from the use of bulky and sophisticated instrument into the use of the card-side potentiostat that allows smartphone detection. As you can see in figure A, here is the real images. And figure B shows the screenshot from the smartphone detection where we test with the monkeypox negative and monkeypox positive. You can see that with the negative one, it clearly gave no electrochemical result. But for the positive, it clearly gave the strong signal on that allow detection on the smartphone. And lastly, we further testing the sample analysis using real viral sample. And the sample was undergone extraction using the standard protocol. And we used a urine and saliva sample as we prioritize the non-invasive sample collection. And from this result, it can demonstrate that we can successfully detect this real extract viral particle in the sample with the cutoff setting at 50 copies per milliliters. And in conclusion, we can conclude that we successfully developed a mismatch-driven DNA biosensor for monkeypox virus detection without the need of amplification and labeling step. And we achieved an LOD of 1.88 in standard control and also 50 copy per milliliters in sample. And the NFC integrated device demonstrates the system readiness for on-site analysis. And it also holds a promise for future adaptation towards strain-level discrimination and also a broader point-of-care pathogen screening. And this work has been published in Electrochemical Acta this year. Finally, I would like to thank the Asahi Glass Foundation for the support and also the Institute of Biotechnology and Genetic Engineering. Thank you.
Thank you very much for your talk. So, any question from the audience, please?
Thank you for your presentation, and I'm interested in the selectivity.
Yes.
Yes. How does the biosensor avoid the cross-reactivity with other virus, such as other pathogen or the herpes and something like that?
Okay. Actually, from the selectivity study, we didn't test with other pox virus, but we test with because we focus on a sexually transmitted disease. But with the pox, we didn't test it. But we have performed the blast with the other pox, and it's turned out that I think there is a cowpox that may have interfere with this system, but it's not found in the sample. Yes, because as I said, we use the sexually transmitted disease sample. Yes.
So, if not, let's thank our last speaker, Dr. Abdul Hadi, again. Thank you very much. And on behalf of the organizing team from Chulalongkorn University, we would like to thank representative from Asahi Glass Foundation for your kind present today at the event, and we hope for your future collaboration in the future. Thank you very much for today, and thank you everyone. Thank you very much.